So, hello everyone. I'm Gyula Fora. I work very closely with Paris on stream processing, fault tolerance, and developing Apache Flink in general. And I would like to pick up where Paris left off and talk about some more of the practical aspects of implementing a streaming application. How do we build up our streaming pipeline so we're not vulnerable to failures in our systems. So just to give an outline of this presentation, first I'm going to show you some general patterns that are recommended when you build a streaming pipeline. Then I will go into some more detail about specific parts of this pipeline, introducing some systems for those parts. And in the second part of the presentation, I will like to give a short demo on actually assembling a small streaming pipeline as an example application using the components that I will discuss in the first half. So let's get started. So we have heard a lot about stream processing already. But one thing that I think that wasn't emphasized yet is that there's actually a huge application shift from static batch processing to the real-time applications. And in my opinion, this is triggered by the sophistication of the available stream processing systems. So now we can actually express much more complex stream processing logic than before. So companies are actually starting to implement their applications to work in real-time fashion. So what this means is that instead of high latency apps, now we get everything in low latency, instant recommendations, instant forecasts, and we're changing our batch processors to stream processors. So we're getting rid of MapReduce in many cases and replacing them by stream processing systems such as Storm or Spark streaming or Flink streaming. But why is this good for us, and what does this mean for our application pipeline? So first, it represents a very different usage pattern. In the traditional batch world, we probably have the same data sources. We still receive event streams, logs, sensor data, but instead of applying the changes continuously, we run a batch computation periodically every couple of hours or every night, which will give us some results that we will dump into a database which will represent the state of the world as we know it at that point, after finishing that batch computation. Now our applications will interact with these databases, and they will query the current state every once in a while as these results get updated. Stream processing turns this into another pattern by, instead of periodically updating our state, we will continuously update them as new data becomes available. So instead of storing the state of the world in a database, we will store the history of the world in a streaming system and continuously update our current state as new data flows in. And what this also makes possible is that as data flows into the system, we push the state updates to the applications so they can get low latency results. And this, of course, results in many nice applications, recommendations, and it's practically all around us. Traffic information becoming available in real time, and so forth. Also, one interesting thing that we need to keep in mind is that stream processing is actually a much more powerful programming model than batch processing because, as we've heard in many talks before, Cosmin highlighted this yesterday in the data flow talk, we can just regard data sets, batch processing, as a special case of streaming, which work on a bounded data stream. All right, so this is very nice, and it seems that we can do good things with that. Probably everybody in the room is now convinced that we should use stream processors. So, but what can go wrong when implementing a streaming application? So, this bowl of spaghetti is the streaming pipeline of LinkedIn in the pre-Kafka times, which actually motivated the development of Kafka as a system that I will introduce later.
So this was LinkedIn, no? LinkedIn.
Yeah, this is the streaming pipeline at LinkedIn a couple of years ago. And you can already see some...
See anything.
yeah, you can see a lot of things and nothing at the same time. So, but what's important to note here is that we receive streams in some form that's at the top of the slide, and we will feed it into different systems. These systems interact with the stream, they transform, they send it to other applications. So there, you can imagine the amount of boilerplate code going on with stitching these different parts together in one system, and it is not scalable. Not scalable in the application sense. So we will inevitably want to add more systems to our processing pipeline as we discover more use cases. So that means we will add it to somewhere here that will be stitched to some other part of our system. And this goes on forever. So how can we make this better? So there's a very nice blog post about this whole idea that you can read. It's on the Confluent blog. These are the people responsible for the continued development of Apache Kafka. And the idea is to separate the stream processing pipeline into different parts. So we will identify 3 parts of a typical streaming pipeline. The first is, of course, the data collection part. This contains our data sources. This can be event logs, sensor data, transaction logs, whatever kind of event stream that you have. And we will feed all the data in some sort of broker system. I will talk about broker system in more detail, but their job is to make the data available for processing. And now that we have the data persisted in our broker, we want to perform some analysis on it. Here we will plug in our stream processors to detect the fire. This can be Storm or Flink or Spark streaming. And of course, these streaming programs, after the analysis, they will produce some results, probably continuously, that we will probably feed back into the broker so we can do further analysis on it or make it available to other systems. So just to recap the stages, gathering is data collection, and it usually involves some sort of integration framework to make the to transform the data in some understandable format for the broker system. A popular open source solution is Apache Camel, which implements the enterprise integration patterns, so to speak. The broker service is the second stage. Here we store the collected data and make it available for streaming analytics. And the broker systems are generally fault-tolerant message queues. The stream analysis is the actual execution of the business logic on the incoming stream, and they may feed the results back into the broker system. I'm not going to talk about the data gathering part, but I will focus more on the broker and streaming analytics part of the system, because data gathering is very application specific, and I don't think I should talk too much about that. So broker system. As I said, broker systems serve as a middleman between data collection and data processing. Their purpose is to decouple the receiving of the data from any external source to the actual processing. This comes with several advantages. It can provide better fault tolerance for the streaming applications. We have had this discussion shortly during several talks. There are stream processors that promise exactly once processing guarantees. This is, of course, impossible without implementing some sort of a broker service that will store the data persistently, because we can always lose our data while receiving it from our external source. And if it cannot replay it to us, then there is no point of having any fancy fault tolerance algorithm, because the data is just lost.
How much overhead does a broker add to the pipeline in general?
Well, if we think about Kafka, I would say not so much. It's always better to use it. I mean, usually not the broker. Broker is not the bottleneck in the system. These have very high read and write throughput because it's just a logging service. So they can use sequential I/O to write it to disk, and that's actually very fast. So here we can see the broker pattern, which is actually resembles the whole streaming pipeline, which also highlights the central position of the broker in the streaming architecture. We have our producers that write to the broker. Producers are the data streams that we receive. And we have different consumers that can subscribe to the broker. These would be stream processors or any application that will use the processed data. So what are the requirements for such a broker system to be practical to use? First and most important is it should be persistent. An ideal broker system should provide durability of our input stream. That means we should be able to replay any set of elements on demand. So if our stream processor would like to replay some data for fault tolerance in case of failure, then the broker system should be able to give the data to it. It should, of course, have high throughput. This is essential so that the broker system does not become the bottleneck of our processing. We generally want this to be fairly lightweight compared to the actual processing pipeline. And of course, we want the broker to be scalable. So in case in the future we add more data sources, or at peak times we might need more storage capacity, we should be able to add new nodes to our broker cluster, and it should scale properly. Of course, flexible APIs help. We should be able to connect it to our processors and data sources. Question?
Does the broker need to be topology aware, network topology aware? For example, you're interested in a set of streams, and your worker, which is interested in those streams, are in the same rack or same?
Well, I guess this goes with fault tolerance and performance at the same time. I guess it's better if you distribute. These brokers usually replicate the data to make it persistent, and that should be network aware, topology aware. And also, it helps if you can get data locality, so you can get much higher read and write throughput. But these systems are usually implemented that way. Yeah. So commonly used broker systems are distributed message queue services, such as Kafka, that I'm going to talk about more. RabbitMQ and ActiveMQ, they all have a queue interface. So let's talk a little bit more about Apache Kafka, which is probably the most widely used broker system currently. And almost all streaming applications use Kafka that use the open source stream processors as well. So what you need to know about Kafka on a high level is it's a distributed partitioned commit log service. It has very high read and write throughput. I'm not going to go into the technical details why it is so, but the main idea is that it uses sequential disk I/O. The main concepts that you need to understand, which I will use in the second half of the presentation, is a Kafka topic. A topic is a specific message queue. It is basically a stream that you write to Kafka. For instance, your sensor data for the temperature sensor. Another topic would be the smoke alerts for the smoke sensor. Producers are units that write to specific Kafka topics. Each topic has more than one partition, and the producer can select which partition to write to, how to partition their data. We have consumers. Consumers read from topics. They can subscribe to topics, and they can be organized into consumer groups, and each message in a specific topic will be sent to exactly one consumer in a consumer group. And the important thing is that all the Kafka topics are partitioned. So in each topic, we have multiple queues, multiple partitions, and we can use this to read and write in parallel. So what kind of guarantees can Kafka provide us? So there you see that the anatomy of a topic. Each topic has different partitions, and in each partition we have a sequence of messages which are strongly ordered, and there is an offset mapping to the records. Kafka provides strong ordering guarantee inside one partition of a specific topic, but there is no ordering guarantee across partitions, so it provides partial ordering guarantee. By default, if we don't do anything else, it provides at least once processing guarantee. So it guarantees the application to send all the data at least once. In order to provide exactly once delivery from Kafka, we of course need some sort of coordination between the consumer and the Kafka broker. This usually means that the consumer needs to acknowledge that he has read up to some specific offset. Because this is exactly for the reason that data can be lost during transmission. So Kafka cannot by itself know when a specific record has been processed by the external system. So for exactly once processing, we always need coordination across the systems.
So with each queue is a topic?
No. In this case, this is one topic. And
Oh, this is one topic.
Exactly.
And one topic, in this case, has 3 partitions. And for fault tolerance purposes, actually, each partition will be replicated on multiple Kafka servers.
So each partition covers a subgroup of sensors, huh?
Yeah.
And if I want to ensure that there is going to be an order, I have to tell it that it shouldn't be, or should use only one partition.
Well, if you want strong ordering, then that can only be guaranteed from one Kafka partition. So what you would probably do is that you, what?
I have to explicitly tell that.
Yeah.
Yes, but ordering, I mean, the most important is the timestamps of the events.
Yeah. But what you can also do is partition the data when you write it to Kafka in a way that you make sure that data that is interesting for you together end up in the same Kafka partition. So when you read them, you can be sure that they come in order. So here's how you run a Kafka cluster. I will not gonna execute these now, but I will do so later. So first, you need to start a Zookeeper server. Kafka uses Zookeeper for distributed coordination. The main purpose is to select a leader partition, as every partition is replicated for fault tolerance purposes. Kafka always needs to know which partition is the leader. So writes are first written to the leader, and the leader replicates it to the replica partitions. And of course, the user only gets a commit acknowledgement when the leader has replicated to the majority of the partitions. So once we have Zookeeper up and running, we can start the Kafka server, or also called as the broker. And then we can create Kafka topics and create consumers and producers to read and write the data from the topics. Any question for the brokers?
So he used Zookeeper to keep the consistency of the partitions, right?
Yes.
No, just to know who is the leader for each replicated partition.
Yeah, but that's actually that is to implement this consistency.
Agree. It's a consensus
Yeah.
service.
So now I'm going to move on to stream processors, just really quickly, as we've seen all the previous presentations. So now we have our data written to Kafka or any other broker system, and we want to do some analysis on it. This is probably where we would implement the application. One can argue that this is the interesting part of the streaming pipeline. But what is interesting to whom, right? So general requirements of a stream processor is it needs to be high throughput, of course. Well, it depends on the application how high throughput we need, but it should be able to keep up with the broker in general. One very important thing about the stream processor is that it should be expressive enough so that we can actually write the application, because if it's too simple, we cannot express many things, then there's no purpose of using it at all. Most of the currently used systems, Storm, Spark Streaming, and Flink, are pretty much equivalent in their expressivity. Some has nicer APIs and make it easier to write specific things, but in principle, they use the same programming model underneath. The processor should be fault tolerant, at least fault tolerant in the sense that if we assume that the broker is fault tolerant, then the stream processor should be able to execute with consistent and correct results, even in case of failures of the stream processor. It should also provide low latency for applications that need it. This is not always necessary, and low latency can mean a variety of things, as we will see it for different stream processors. There are, of course, plenty of stream processing systems available. Some of them are open source, some of them are commercial alternatives. But I will only touch on 3 of them, and they're all open source: Storm, Flink, and Spark Streaming. So Apache Storm is what usually comes into people's minds when they talk about distributed stream processing in the Apache world. This was practically the first distributed stream processing system that became widely adopted. It provides a true data streaming model. That means that we assemble this graph of computations, and records flow through this graph and are processed element by element. It provides very low processing latency, which is around tens of milliseconds. So let's say around like 30 milliseconds is what you can expect for a lightweight streaming pipeline. But of course, this comes with a slightly lower throughput as well. As Paris has already shown, it has a pretty low-level API where we actually program against this distributed data flow. We assemble this graph from the vertices, and then we need to connect them by the edges. By default, it provides at least once processing guarantees, and it does that by tracking each record flowing through the topology, and if a record fails, it will be replayed from the sources, which will cause it to replay it on some operators multiple times in case of failures. So I'm going to show you the word count example in each of these systems. This is not a standard batch word count. This is a rolling word count, which will update the results continuously as we receive a new word. So first time we receive Apple, it's going to output Apple 1. Next time it's Apple 2, and so forth. So in the standard Storm API, we have seen already in Paris' presentation, we define create a topology builder, which will let us create these vertices and edges in the processing graph. Then we create the spouts, which are the sources in this acyclic graph. So here we create a spout that will output random sentences with a parallelism of 5. Then we will create the other 2 bolts that will do the actual word count. We need a bolt for splitting the sentences that we will call split. The logic will be programmed in this split sentence instance. I left it out from the presentation, but it's quite lengthy. This one will have parallelism of 8 and is shuffle grouped to the source. That means we don't care how data is coming, how data will be routed from the source to the parallel instances of this splitter operator. Last, we need to define the counter, which will contain which hold a hash map of the current counts, and we connect that to the splitter and with fields grouping, ensuring that each word will land at the same parallel instance of this counter. Those are the parallelism hints for that operator. So that means we will create 5 parallel instances of this source, here 8 and here 12. We expect this to be the more heavy operation, so we want to parallelize it more. Alternatively, one can use the Trident API, which provides a more functional approach. Unfortunately, Trident never got really popular, so I don't think they're spending too much effort on further developing it. Here we can see the same approach that we find on systems like Flink and Spark, where we create streams and apply higher order functions to transform these streams. All right, that's it about Storm. I'm going to move to Apache Flink. Apache Flink in the runtime level is also a true streaming engine. It also assembles a distributed data flow graph from the program that you have written. In Flink's case, you don't actually need to write the vertices of this graph, but instead you use a high-level functional API, which will be translated by an optimization layer to this distributed data flow. As we've heard earlier, this has the advantage of allowing optimizations to be carried out by the system itself. And this actually, so in Flink's case, and this is also true for Spark and all the high-level declarative languages, the system actually knows something about what's going on. It has some sort of understanding of the program, so it can make nicer optimizations. Flink, the unique thing I would like to highlight in Flink streaming is that it provides a very flexible API for defining stateful operations. If you think about Storm's way of writing a word counter instance, you will probably have a hash map field that would be lost upon failure. In Flink, you can declare what is your state at the operator, so it will be checkpointed during the fault tolerance mechanism. Flink also lets you define flexible windowing. The API is not as sophisticated as in case of Google Cloud Dataflow, but we're working hard to get there. And Flink provides exactly once processing guarantees. Paris has already talked about this. Flink takes periodic global snapshots of the execution so that in case of failure, the system can fall back to a previous complete snapshot and continue the processing from there. You have seen this at least 3 times already. So this is the rolling word count in Flink that we've seen in Storm. Here we define our stream reading from a socket. Then we split the words using a flat map transformation. And we map the words to a Scala case class for convenience here, which will contain the word itself and the count instead of just using plain tuple 2s. The nice thing that comes out of this is that now we can group by the string reference of the case class field and then sum the frequency. One thing I would like to add here is the window word count. I omitted this for Storm because this needs to be custom implemented, as Paris already highlighted, which will definitely not fit on the presentation slide. But Flink, similarly to Cloud Dataflow, has a very flexible API for defining windows and the streams. Here, we append this line in the middle, which will create windows of size 5 seconds, which will be triggered every 1 second. So it's practically a sliding window of 5 seconds. And we will now execute the word count inside those windows. So let's move to Spark Streaming. Spark Streaming takes a radically different approach to stream processing as opposed to Storm and Flink. It uses Spark as the underlying system, which is inherently a batch processing system. So what happens for Spark streaming programs is that streams are discretized into small batches of records, micro batches, which are represented as Spark RDDs. And we apply batch computations over each micro batch. The advantage of this approach, of course, that it can get very high throughput, probably the highest among the other streaming systems. But it, of course, comes with slightly higher processing latency because of the batching of the records. But this is usually not a problem for almost all the applications. The latency that you can get from Spark streaming is perfectly fine. It's usually in the order of hundreds of milliseconds. So it's still not a high processing latency. Like Flink, Spark also has a very nice functional API. And in addition to Flink, what it can also provide by using its batch runtime is that it can give some nice integration of batch and streaming programs. We can just join simple RDDs, simple batch data sets with streaming RDDs. It also gives exactly once processing guarantees using the same mechanism as a standard Spark batch runtime uses. Going to the same word count application, here we can see that the program that we write for Spark streaming is very much similar to what we had in Flink. But one thing that you should notice is that here I put window word count on the top. So actually, the program that looks like Flink rolling word count is in Spark streaming, that is the window word count. And this is exactly because Spark uses micro batches and executes the computation that we define on each micro batch. So what we have here, splitting the lines, counting the words, is executed for each micro batch, which maps to a window in the data stream. You can, of course, define the window size in Spark as well in terms of processing time. If you want to
do real rolling, let's see. If you want to do rolling window count.
I'm getting to it. It's right here. So if you want to do rolling word count in Spark, you could definitely get the exact same results as you would get in Flink, but the implementation is rather complicated. But what you can do in Spark instead of a true rolling word count is that you do a rolling word count where you actually get the results after receiving each micro batch, which can be implemented by using the update state by key method, which lets you update a state that is kept for a specific key in the data by receiving the tuples for the next micro batch and applying an update function to the state. So in this case, the state for each key is stored as an RDD as well. So let's put all these things together and see how different parts fit together in some nice application. So first, I would like to show you some concrete use case where the pipeline that I was talking about is used in production. So here's the streaming pipeline as used in Bouygues Telecom. It's a French telecom company. And what they would like to do is they receive network data from their network infrastructure and also user data from their subscribers. And they, of course, want to transform it, analyze it, derive some statistics of it. And also, they want to trigger some alarms when something goes bad in the system. Maybe the network breaks or something else. Or users are getting increasingly dissatisfied. That can also mean that something has gone wrong. So the way the pipeline is assembled at Bouygues Telecom is that they take their data streams, use Apache Camel as their integration framework, and feed the data into Apache Kafka. To this data, they deploy a Flink processing job that will analyze the incoming streams, generate some statistics, and also trigger real-time alerts in the system. So in this case, it's very important that they can get the alerts as fast as possible. So that's why they have chosen Flink to get a very low latency. But we could probably substitute it with Spark streaming and get similar results. The results of the computation of the streaming pipeline are again fed back into Kafka. We could have drawn this slightly differently and put these two together, but this is done like this just for the sake of easy understanding. And now other systems can query the results for the website, for search, and other things that you can imagine. You can read more about this specific example in the Data Artisans website. They have a nice blog post about that. All right. So in the rest of the presentation, I would like to show a short demo on actually assembling a streaming pipeline that will use a combination of a broker system, Flink, and some Python analysis to get some insight about the data. Due to the lack of time, I will skip the money part. I will leave that to everyone to go home and earn some money by stream processing. So what are we gonna do? We're gonna generate some data streams and write it into Kafka. We will start a Flink processing job that will fetch the data as it comes into Kafka and generate some statistics. We will dump the results back to Kafka, and then we will use an IPython notebook to visualize the results of our computations. Okay, before I start, does anyone have any questions to what I've said so far? That's good. So the material that I'm using for this demo can be found on GitHub. On this website. So I encourage everyone to go there, check it out. I've written the descriptions down step by step, so everyone should be able to execute them home alone. It shouldn't take more than 15, 20 minutes. All right. So if we look at this GitHub repository, this gives a description of what we'd like to do. And the actual use case that we would like to analyze is that we receive temperature data. Coincidentally, this is temperatures as well, but it has nothing to do with Paris's presentation. So these are temperature data for European cities. It has absolutely no connection to the real-world temperatures. I generate them randomly, drawing them from Gaussian distributions. But in anyways, we will generate these temperature data in the form of simple textual data that will contain the city and the current temperature as a measurement, and we will dump these into Kafka. So next thing we want to do is write a Flink program that will read and parse these strings, convert it to some format that can be understood for further analysis. The format will be tuple 2s, of course, city and temperature. And then we will do two simple things. First, we would like to do a rolling average for each city of the historical weather data. Again, this is not something very practical. No one cares about the all-time average. But you will also find this somewhere recorded anyway. So here we will actually compute that. So first you receive 30 for Budapest and then 40. So that gives you a cumulative average of 35 and so forth. We will do this separately for each city. Another thing that we would like to do is compute to get the hottest place in Europe by periodically querying the current maximum temperature in 5-second windows. So that will give us an idea where you shouldn't go, why you should stay in Stockholm in 20 degrees instead of enjoying summer. And the last thing, so these results will be dumped into Kafka. And what we would like to do at the end is start an IPython notebook and actually fetch these results, do some visualization. Yeah, and this will happen more or less. So the first thing I would like to show is the actual Flink program that will do the processing before starting up all the clusters. So our Flink program is a rather simple Flink topology, but it may be slightly more elaborate than the previous examples. So let's look at the parts of a streaming program that are needed to generate these results. This is the Flink Scala API. Is the font size large enough to see for everyone?
Can you make it a little bit larger for them, maybe? Or
Is it okay? Is it not okay for anyone?
What does the back row say? That's the important question.
Back row. You see?
Back row, yes or no?
They're not following. So we start out with creating an execution environment. This is a stream execution environment. With calling the getExecution environment method, we will get the current environment for the actual execution. So if we execute this from our IDE, this will start a Flink mini cluster. If we deploy this jar on a running Flink cluster, this will fetch the cluster environment. So now that we have our environment, we can start defining our data streams. So first, of course, we want to define our source stream. This is the data flowing in from Kafka. You can think about it, the temperature data coming as strings into the system. So the source is a Kafka source connected to the local Kafka instance running. And we will use a simple string schema to decode the messages because we know that they're coming in a string format. Next thing we would like to do is parse the incoming data. One thing we need to make sure is that our parser is not vulnerable to malformatted data, so it's not going to take down our whole Flink topology if a bad record arrives. So in this case, we use the either type to distinguish correctly parsed records from parsing errors. So we will technically catch any exception that has occurred during the parsing. And in that case, we will just store the string that caused the parsing error.
So what is the output of the parsing, the stream?
The output of this is a data stream of this type. So next thing we would like to do is actually separate the correctly parsed records from the parsing errors. For the errors, we will just print them to the console. We will not do anything else with them. In an actual real-world application, you will probably want to know what happened, but we don't care for now. Also, we will filter out the correctly parsed records that will actually give us a data stream of temperatures. Temp here is a case class instance which contains the city and the temperature.
So you can say the first phase is like a cleaning phase.
Yeah, this is the
You have to
cleaning.
do anyway.
Yes. So now we're at this point, having parsed the temperatures, and we have a stream of correctly formatted temperature data. Now the first thing that we would like to do, as I said earlier, is compute a rolling average. Paris has already touched briefly on this topic. So the rolling average is a stateful computation where we keep a state for each, in this case, each specific city. So what is the state that we need to keep here? I use a data type called average state. It's a state for the average. It's maybe not the best naming. But the point is that we need to store the sum of the received temperatures for the specific input, and also the count that we have received so far. So we will apply a key. We will partition our temperatures by city, and we will apply a stateful map transformation that will keep an average state for each specific city in the data stream. And now we can define our stateful map, which will take as input the next element, next temperature, and the current state, and output the output element and the updated state. So we can get the current state from the input of the function. If it's none, that means this is the first element that we see for the city. We initialize the state to 0, 0. Now we update the state by adding the current temperature to the total sum and incrementing the count for that specific city. And now it's time to compute the average that we would output, the next average in our cumulative average for this city. We simply create a new temperature data containing the city of the input, and we take the sum and the count from the updated state. So now we just need to return the results, return this tuple 2, first return the average, and then the updated state.
And sum is like because of the type ISER, right?
Yeah, the sum is because we use this state, this case class, which contains the sum.
Okay.
The sum, I think.
It's sum.
It's
I mean,
sum
the type
and the average, and then the sum.
Oh, sum. Yeah. That's the option. That's for the Scala options. Yeah. No, yeah, it's option. It's an optional type.
The optional.
So it's either sum or none.
Okay, good. Just to remember.
Yeah. We could also use pattern matching here, but this is probably simpler. Here I added an additional step that is not motivated by the use case, is that we will filter out random elements from our output stream, because we probably are not interested in all the rolling updates. So what this filter will do is keep approximately 10% of the data as output. So now we have created our average temperature stream. What we would also like to do is create our global maximum stream that will be a window maximum over 5-second windows, which can be written simply as this. So we create a temperature, create a tumbling window of 5 seconds. So windows don't overlap, but are followed by each other. And then we get the maximum temperature max by the temperature itself. So this will, for every 5 seconds, it will return us a temperature instance which had the highest temperature during the last 5 seconds. We also need to flatten the windows, because the result of this computation is a window, and we want to convert it back to a proper data stream, so we're flattening the results. So now the only thing that remains is to add 2 sinks to write the results to different Kafka topics. We read the input from the input topic, and now we're gonna write the outputs to output average and output max. These are the names of the Kafka topics that will receive the results. So in this case, our Flink program works as a Kafka consumer in the sources, and also a Kafka producer at the sinks. And now that we have assembled our topology, we can execute the streaming program, and this will fire up the parallel processing pipeline. All right.
Very nice.
So let me show you how this works in practice. I'm just going to copy paste the code to make sure I don't mistype anything. So first, as we've seen, we need to start a Zookeeper server. Okay, it's done. I'm going to do everything in the local cluster. This can be, of course, done in a proper standalone cluster, but it's slightly more complicated. So now that we have Zookeeper up and running, we need to start the Kafka brokers, the Kafka server. That's also a simple command. All the configuration parameters can be found in this server properties file. I will not go into the details. Everyone can read about it in the Kafka documentation. So this has started the Kafka server. Now it's time to actually create our topics that we would like to read and write. Topics are also persisted between different Kafka executions. So even if you shut down your Kafka clusters, your topics will remain there. Defining topics is slightly more verbose than starting the cluster. So here we can see what we need to define for each topic. We first need to tell the system that we would like to create a topic with the name input, with number of partitions. Here in this case, I'm going to just create 1 partitions and set the replication factor to 1. This is not fault tolerant at all, but for the sake of the demonstration, it's perfectly fine. And we also need to define the host name for the Zookeeper server. These are the minimal things that you need to define for each topic. There are no default values for these parameters. So if we run this command, we run this line, it tells us that it has created the topic input. And now we can create the topics for the outputs as well. We create one for the average, and then we create one for the maximum. We can also ask Kafka what topics we have already created. So that can be done by the following command code. By calling list for the topics. And here we also need to give the Zookeeper hostname as parameter. Oops, almost. That's why I'm copying.
Yeah, it's better to copy.
Yeah.
That's fine.
So the 181 is the end of the line. So here we can see that the topics have been actually created: input, output average, and output maximum. So now it's time to start our programs. First, I'm going to start the Flink program that will read process data from Kafka, which can be done after building the jar. The steps required for that can be found also in the description, but I've already done that. So here I'm executing the Flink program as a simple Java program, the jar. This means the get execution environment will return a Flink mini cluster. So this is equivalent to executing it from an IDE. You can think about this. But I could have deployed this Flink jar to an already running Flink mini cluster. So if you're interested, I can show you offline. It's practically the same complexity. So now we can see that we have a couple of components up and running from the Flink cluster, everything with parallelism of 8, because by default it uses the number of cores that you have. Okay, but this probably not produces any results because we're not feeding data into Kafka. So now this Flink program is running and probably hanging in the sources, waiting for for any data to come from Kafka. So what we need to do is actually generate some data. And I've written a simple Scala program that will generate random temperature data for each city. And also here is how you deploy to a Flink cluster. So here you would start the Flink cluster in the streaming mode. Then you can use the run command to actually deploy the jar file. So now we will start the data generator. It tells us that it makes some progress, so that's nice. So here, this is still running, but we don't see any outputs because we have written everything to Kafka, so we're not printing anything. We print the parsing errors, but unfortunately, I wasn't smart enough to generate parsing errors, so we will not see them here. So hopefully, everything is in Kafka now. So let's find out. Let's start a simple Python notebook to actually query the results that we've generated.
So you mean now we are going to look to the Kafka output?
Yeah, now we're going to look at the output of the processing system.
Yeah, exactly.
So I'm using the Kafka Python library to create create a simple Kafka consumer, and it will be executed in 2 Python processes. And what we would like to achieve here is that, okay, maybe this is too small.
Nice, like that.
All right. So we have 2 local variables, average temperatures, which is a dictionary, and max temperatures, which is a Python list. In this dictionary, we will continuously update the current rolling average. So every time we receive a new value, we will just replace the old value in this dictionary. And with the maximum temperatures, we're just going to append them to the end of the list, so we can visualize it as time series. So trust me that this works, as we will see. And now what we want to do is we can just plot the data inside this max temperatures list. We use the matplotlib library.
We should have reset the whole execution. Are you going to try it? Or?
No. These are the data that has been generated since I started the program.
Ah, I see. Oh.
So now if I execute it more times, you can see it is continuously updating. So you can imagine building models, new models in Python, trying out things as your data evolves. We can also look at the dictionary in a nicer format. So here we can see some data. So it's not very realistic, as you can see.
So
but
when you started the notebook, you executed everything.
when I started the notebook, I just started this Kafka consumer,
Yeah.
which
You execute all the cells.
yes. So I started the Kafka consumer, which will continuously push data and update these 2 variables. And now every time I access them, they will have the updated results. I'm not completely sure about thread safety here, so how this works in Python, but I think this should be thread safe. But this is just for the demonstration. So this was pretty much it as for the demo. So I have one last slide in my presentation, and I think I'm in time almost. So what have we learned today? Building a proper streaming application and a streaming pipeline is not as trivial as it sounds in the first place. We need to take care of some specific parts to make sure that the whole system will function properly, even in case of failures, and to make sure that our application that we're developing is actually scalable for our future needs. Stream processors are just part of this big picture, and broker systems play a key role in designing streaming pipelines. And currently, there is no single open source solution to provide an end-to-end pipeline for all our application needs. And this is because there are so many different applications that needs to interact with different systems. It is hard to design a system that can do everything. So we will always try to mix and match the components in a way that it suits our application the most. But we need to keep in mind some specific patterns in general to make this viable. So thank you very much.
Thank you very much.